Both presenter available, so we will move on to the next talk, which is by Buti Nkosi. He's from the university, Wits University, and he will speak to us about observability of neutrinos from quiescent blazars, the KM trinet.
Okay, thanks, James, for the introduction. As James said, my name is Puti, and I'm here on the behalf of the KM3Net collaboration from Wits University. And yeah, so um, the main aims was to determine the detectability of neutrinos from quiescent blazars. The reason behind this is actually the reason behind this is because all of the blazars that have been confirmed to be neutrino sources were all in flaring states. So if we are able to detect neutrinos from quiescent blazars, then uh, then we'll be able to learn about the environment where the jet or the blazars, about the environment of the blazars, because in most cases blazars blazar spends more time in quiescent state than in flaring state. Then the second reason why we wanna do this kind of a research, it's because we wanna know about the nature of the blazar jet emissions, where jet emissions can be explained in two types of models. I'll introduce them soon. Okay, so the first part I want to talk about is the KM3 net. What is the KM3 net? The KM3 net is like a second generation neutrino telescopes. Um, the collaboration itself is made up of 55 institutes and groups around 16 countries. 6 institutes are from Africa, 3 of which are from South Africa, and I must say the other 3 they're from Morocco. So the telescope are located in the Mediterranean Sea. If you look here, where there's the arrow, I think somewhere close to Barcelona. This is where the Orca telescope is located, where it's gonna be mainly used for oscillation research, and this is the this is the Arca telescope, which is gonna be used for astroparticle research. And then this other dot here, I think that's the Antares, because the KM3 net is just a successor to the Antares. And also, it is important to note that it's still under construction. So, how does it work? So, what it does, it detects Cherenkov radiation from the interaction of the muons and water molecules. So each the Cherenkov light is detected by a photo multiplier tube inside a digital dome. So this is a digital dome. It's made up of photo multiplier tubes, and there are 31 of them. And then these domes um, are going to be mounted into the sea around 3,500 meters deep into the sea, where um 18 of them are connected to form what we call a detection unit or a string. So this is the detection unit. And if you look at the picture here, this is when, I think, last year, March or April, when they were mounting one of the Orca telescopes. So at the moment, um, ARCA has 24 detection units which are in operation, and ORCA has 10 detection units which are in operation. And at the end, the main goal is to have 230 detection units for ARCA and 115 detection units for ORCA. Okay. Why am I using the Geometry net for this type of research? Um, the challenges that we've discovered about neutrinos is that every time when there was a detection made, you always had like a low neutrino flux, and a larger detection area was needed. And the reason why it's also hard to detect neutrinos is that you have atmospheric muons, which act as some sort of background, making it hard to detect neutrinos. So it's either you go into ice or you go into water. And so what are the advantages of using the KM3 net? The KM3 net will cover several cubic kilometers, and it is mounted in deep into the sea, which means the atmospheric muons won't provide that much of a background. And another thing about the KM3 net, it's like, unlike the Ice Cube, which is already operational, it uses it tracks two types of events, where there's like a track-like event and a shower-like event. Where a track-like event, it's when you have a charged particle, like a muon, interacting with the water molecules, and they they look at the track of that charged particle. And then the second type of event that they detect is the shower-like event. So you will have it's almost the same thing that happens with atmospheric neutrinos, where you have maybe some radiation from the sun colliding with the atmosphere and creating particle showers. So even with the detector inside water, you expect the particles to collide, and you have some then you have a shower-like event where and in this shower-like event, you are able to detect all different types of neutrino flavors and the charged particles. Okay, so what are blazars? All right, I think the best way to describe a blazer, or not, might not be the best, but when you look at the unified AGN model, um, if you are looking straight on into the jet, then you see the blazer, which means like a blazer, you can sort of say a blazer is some kind of AGN with the relativistic jets in our line of sight. And as I've already mentioned, a blazer can be found in flaring or non-flaring state. Uh, but the difference between the two is that it spends most of its lifetime in a non-flaring state. So also blazers can be classified into two types, where you have BLX and the flat radio spectrum quasars. And then some observational properties of the blazars would be like the double peak SED, where you find the lower frequency peak is ranges from the radio to the X-ray, and the higher frequency peak ranges from X-ray to gamma ray. And the polarization in radio acts as evidence to the presence of the magnetic field. Just like any bright source, blazars observed to be point sources. Okay, so one might ask, how am I gonna do this? So the first part was to find a blazer jet model. So, and it is important to note that there are two types of blazer jet models. We have leptonic models and hadronic model, which I'm going to explain right now. So, if you look at the SED of a blazer, the first peak here, or the first portion, can be explained in terms of electron or positron synchrotron radiation. And the second peak, that's the one that is a bit controversial right now. It can be explained using two types of models. You can either explain it using a leptonic model, and explain it using the hadronic model, where the leptonic model is it's mostly Compton radiation. So you have so in leptonic models, you might have synchrotron Compton, where the radiation from the synchrotron emission acts as seed photons to as seed photons, and then they will have like 2 minutes. Okay, okay, then I have to move quick. So in order to do this, we used a leptohadronic model that was provided by Michael Zacharias. So one thing to note from this model, it you have to solve the Fokker-Planck equation, and for each particle species is given by this expression, and for the photon density is given by this expression. And the external photons are from the accretion disk, the dust torus, the cosmic microwave background, and the broadline region. Um, okay, so what this code does, or this model does, it uses it's a model where you use it has a lot of free parameters. So all these parameters are free parameters. And we used 3C279 as a guide. Okay, so the first results that we got were not this. Okay, but right now we're sitting at this where you can see with the SED, the first peak can be explained using the electron synchrotron, but the second peak cannot be explained using. Okay, the second peak is it is explained using the inverse Compton from the BLR. It's dominated by that, and and other uh, inverse Comptons from the dusty torus and the disk, the accretion disk. But the hadronic component is a bit low, and these are the neutrino fluxes that you expect from this type of SED. One thing I should mention about this um, model is that the SED that you see here is the SED that we would expect to observe here on Earth, meaning that even with the neutrinos, hence why I only showed one neutrino flavor, all the flavors will be the same because we assume that all the neutrinos will oscillate, and at the end you have the same fluxes for all neutrinos flavors. Okay, so um, I don't think I had enough time to talk about the model itself, but it's okay. So now, one thing we should note is that in most blazer jet emission models, they are always constrained by the variability. But I wasn't interested in the variability, and so I had to assume a longer time scale. So in Blazer Jet, you get the emission region to be of orders 10 to the 15 centimeters, depending on the variability. But now, assuming that we want the blazer to be in quiescent state for a very long time, so you're just gonna increase the emission region and make it bigger so that you allow the particles to interact as much as they can. And the hadronic component, like I said, it can be used to explain the neutrinos in blazars, but now the contribution was a bit low in this situation. Hence, we intend on increasing the hadronic contribution and want to see what does that do to the neutrino fluxes. And the next step, because unfortunately I couldn't show the other results because it had to be audited before I present here. So the next step of this was to show you the bint analysis of the fluxes, which I don't have with me right now. Thank you for listening.
Thank you very much, Buti. Do we have questions? Yes, please.
I'm Joshua, and I want to ask that. So, according to your research, apart from the relativistic jets from gamma ray bursts, you can also detect neutrinos from blazar models. Are you proposing the models, or is already there?
The model is already there.
Okay.
So, or what I can say is that the model is already there. they normally use the model to study the SEDs of blazars and other similar kind of AGNs.
Okay, but are you able to detect neutrinos from this model?
This is just a simulation. So in order to detect neutrinos, you will need to perform the actual observations. Yes.
Okay. Right. And does your research has anything to do with matter-antimatter symmetry?
Sorry?
Does your research has anything to do with matter-antimatter symmetry?
No.
Okay. Okay. Thank you.
There's a mic there.
Question. So using the ARCA detector, which is quite few years away, isn't it? I mean, you are not in there. They have just started putting the first detectors. What is that real? You could possibly get those neutrinos detected. I mean, have you have the threshold of detectability is reached for those low for the neutrinos from the quiescent blazars from the simulation you made? I mean, that's
Oh, okay. We just ran the simulation, and at the moment we are like in a stage where we'll just use the results from the simulation and use it to the response function in order to see if we'll be able to get that. But as for the sensitivities of ARCA itself, I think they might be able to detect because it goes from MEVs to PEVs.
Thank you, Bhuti. Do or will ORCA and ARCA detect solar neutrinos, and if so, what do you do with them?
Okay. Okay. So, thanks for the question. ARCA is for astroparticle neutrinos, right? Research, sorry, and then ORCA is for oscillation research. So ORCA is the one that is like it's a specialized detector for for mainly particle physics, the oscillations. So what they do, they look at low energy neutrinos, which are from the sun. So you can do the neutrino mass ordering, neutrino oscillation. How does it come about? Just using the ORCA.
Okay, thank you. Maybe I take just the last question.
Okay.
Can you comment briefly on the proton synchrotron radiation in your model and why you chose 3C279 as your standard candle for the modeling?
Okay. Let me start with why I chose 3C279. I had three sources, so three different type of sources. So two of them were confirmed as neutrino sources. The first one was so we had like three. It was one BLEC and another an FSRQ and 3C279. So with the other two, I couldn't get the right parameters in order for it to converge. So with 3C279, the reason behind that was there's been a lot of research done on it. There are a lot of models on 3C279. So I leveraged that. I'm like, okay, so if there's a lot of work that's been done on 3279, then it's a good candidate to also look at. Okay. Thank you.
Do we have to share screen from here? Yeah, okay. So the next speaker would be Isaac, who is already online. He will be presenting remotely. Isaac is from University of the Free State here in South Africa, and he will speak to us about modeling the synchrotron self-absorption from RMHD simulations of relativistic jets using Pluto Lagrangian particle module. Isaac, could you please share your screen? Okay, good. You have the floor.
Good morning, everyone. Can I maybe just get a quick indication if I'm audible?
Yeah, we can hear you clearly.
Okay. Thank you. All right. So as mentioned, I'll be talking about modeling synchrotron emission and self-absorption from. Sorry, could you just?
You have a few panels blocking your slides in some sections.
Okay.
Can you see the gray thing? Maybe you need to move some things off the screen.
Is that better?
Yes. A few more.
Okay. All right. So as mentioned, I'll be talking about modeling the synchron emission and self-absorption from AGN jet simulations using the new particle hybrid module in the Pluto code. So before we begin, just a quick overview of AGNs. So AGNs are active cores in galaxies where you have a supermassive black hole that's actively accreting matter. And this is associated then also with outflows from that central engine. Now, usually we divide AGNs into different types and categories, depending on both the morphology of the AGN itself, as well as the viewing angle that we observe it with. So in terms of morphology, you typically get radio loud and radio quiet AGNs. In this study, we are more interested in radio loud AGNs, which produce relativistic jets that we would like to simulate. In terms of viewing angle, if you look at it, an AGN perpendicular to the axis of the jet, you'll see something like a radio galaxy, whereas if you look at it along the axis of the jet, you'll see something like a blazon. So viewing angle plays an important role, and this is of course because of Doppler boosting of the relativistic jets. Now, of course, these jets are also quite variable over both long and short terms, which is also something that we would like to investigate. If we look at the spectral energy distribution of these AGN jets, they produce emission over most of the electromagnetic spectrum, with the lower energy emission or the lower energy hump being attributed to synchrotron radiation. And then the higher energy emission, as mentioned in the previous talk, can be produced either by inverse Compton scattering from either the synchrotron photons or external photons, or it could be a combination then of hadronic processes. So we can simulate the large-scale structure of these AGN jets by using numerical fluid dynamics. However, when it comes to the emission processes occur on a micro scale that has to do with the electron distribution inside your AGN jet. And so we can't really recover the emission processes from these large scale fluid dynamic simulations that we use. So in order to better model the emission processes, we are implementing the new hybrid particle module in the Pluto code, which I'll talk a bit more about later in the presentation. So to do our simulation, we chose a full 3D relativistic magnetohydrodynamic jet simulation, in which our model contained a Cartesian grid of 64 by 64 by 256 length units. We assigned a profiled stationary ambient medium to this environment in order to simulate the intergalactic medium that you would have. And then we injected a jet material through a nozzle at the lower Z boundary of our domain. And our jet nozzle had a radius of 1 unit. The jet material that we injected had a Lorentz factor of 10. We considered a beam density or beam to ambient density ratio of 10 to the -3. And we had a helical magnetic field of about 1 microgauss. So we are considering the large scale dimensions of these jets. So on the outer kiloparsec scales. And the flow of the jet material was supersonic with a Mach number of 10. For the simulation, we used a pressure match model with the linear reconstruction and the HLD Riemann solver. And then our resolution we ran out for the simulation was 4 cells per jet radius or unit length. Okay, and this is two-dimensional slices of what this simulation looks like. So on the left-hand side, you can see our density plot as it progresses with time. The center one shows the velocity, and on the right-hand side, we have the pressure. So in terms of the structure of the jet, you can see that we produce a collimated beam of material propagating through our ambient medium. And this beam of material remains relativistic throughout the simulation. And we can see that if we look at the pressure diagram, that we have a sort of shock front forming around our jet structure. And then as the material propagates upward and hits the shock front at the head of the jet, it gets deflected back down and forms a backflow surrounding the central collimated beam. This is also commonly, we refer to this as the cocoon region of the jet. Okay, so now the next step was to use this particle hybrid framework that I talked about. And in this case, this is a new module developed by Bhargav Vidya and his collaborators that's currently non-public. And in this module, we inject then sort of separate tracer particle entities into our fluid. These particle entities then follow the fluid streamlines when you evolve them with time. And then each one of these particles actually represents an ensemble of electrons with some finite energy distribution. We can then evolve this energy distribution with time, evolving the Fokker-Planck equation, taking into account things like radiative losses, adiabatic expansion, and of course, things like second order Fermi acceleration as well. That is important for AGN jets. It's important to note that these Lagrangian particles we're injecting has no back reaction on the fluid, so their distribution won't affect any of the fluid parameters. So we can use this to calculate the emission and absorption. The emission is already built into the code or the emissivity. Already built into the code. We added the absorption coefficient recently, taking into account, of course, all of your relativistic transformations that you have to do since you're working with a relativistic environment. So before we injected these particles into our jet simulation, we first did a consistency check where we just considered a simple one-zone model. And for this case, we can then compare what we get from our simulation to a semi-analytical model that we've set up. So for a one-zone model, we had a size of about 10 to the 16 centimeters. We broke it up into 9 by 9 uniform cells, and we calculated the emission and absorption coefficients at different frequencies, which we can then plot and compare to our semi-analytical model. In case of our parameters for our one-zone model, we have a magnetic field of 1 Gauss, a Lorentz factor of 10. We have a single power law distribution for our initial electrons, and we consider an index of 2.2 with a minimum energy of 10 to the 2 and a maximum energy of 10 to the 7. So comparing our simulation of these particles to our semi-analytical model, here the graphs, the dashed line is our semi-analytical model, and the data points then is what we got from Pluto. And you can see they compare reasonably well. In terms of the emission and absorption coefficients, we have slightly less in the higher energy or higher frequency range. This is mostly due to the fact that the particles are being evolved with time. So there is some cooling and they don't remain at a power law state. Then for our spectral energy distribution, you can see how that compares. We have a slight overestimation here in 10 to the 9, 10 to the 10 frequency range. Okay, so we can then go and inject our particles into our simulation. And here on the right, I have a graph showing what that would look like as the particles propagate through our environment. We inject about 324 particles per time step. These particles are injected at random positions inside our jet nozzle, and the energy distribution, we have a single power law distribution with a index of 2.1, minimum energy of 10 to the power 2, maximum of 10 to the power 7, and we then normalize the density of these particles as well as the energy density based on the fluid, the thermal fluid that we are simulating. We also have a delayed injection model, so we let the simulation evolve for a number of time steps before we start injecting particles into our jet. Okay, so using that, we can actually look at the emission coefficients, and we can do this for a range of frequencies. Of course, this is all still in the synchrotron range. So you can see that for a frequency of 0.15 gigahertz here, you can see that this is now looking at an angle of 90 degrees. You can see the collimated jet, so emission from the collimated jet. And then you also see emission from sort of the cocoon region or the outer edges of the cocoon region, which is occurs because the particles reach the shock front at the head of the jet and sort of get re-energized or accelerated in that shock front. Looking at the different frequencies, you can see that as we increase in the frequency range, our sort of emission becomes fainter. So for example, here at 10 to the power 2 gigahertz, you can see that the initial beam of the jet fades quite fast. And that is simply because of the cooling of the particles. And then once it reaches the jet head, here it gets re-accelerated again. Then moving up even to higher frequencies, so this is in the optical range, you can see that we don't really have emission, which is sort of what we would expect for a radio galaxy with a viewing angle perpendicular to the jet axis. So if we can also look at some other information. So here we have our emission coefficients again for 0.15 gigahertz. But we can also plot our absorption coefficients as well as Stokes parameters. So I didn't really have time to go too much into this, but we can retrieve then the Stokes parameters of our synchrotron emission. So here we have Stokes Q and Stokes U, which we can then go and compare to observations and see how that compares. Finally, we can integrate those emissivity and absorption coefficients through our domain to produce intensity maps at different arbitrary angles. And here I've plotted for 3 angles. So we have for 90 degrees, you can see sort of a radio jet, and this looks more like a FR2 type radio jet. You can see that the cocoon region, the surrounding diffuse emission is non-uniform, and we have sort of hotspots and filaments present there. If we move to a lower angle, you can see that the jet emission becomes more dominant in the intensity map, and this is because of Doppler boosting, of course. And you can also see then a hotspot here at the head of the jet where the particles then interact with shock front. And then at the 0 degree angle, you can see not really much. One thing to note is that our maximum emission is increasing for these angles due to Doppler boosting. Okay, and I would like to sort of make my concluding remarks then. So we are currently running some higher resolution tests. The initial test that I showed was still lower resolution. And we would like to see how it really looks at higher resolution. And we're also busy investigating sort of the spectral indexes in the intensity maps to see how that changes. One thing we would also like to do then in the future is compare this to different sort of models for the, and maybe we can reproduce our FR1 versus FR2 type dichotomy that we see in radio galaxies. We're also currently looking at sort of variable injection, and this is something that one of the other postgraduate students here at the University of the Free State is currently looking at. So Daniel Kulik is investigating this sort of clumpy ejector in your AGN jet, that if you have some sort of blob or knot that's injected in, how does that interact with sort of standing shocks in your jet, and what is the resulting emission that it will produce? And we are trying to sort of reproduce flare states in blazars that has been observed. The final thing is for future work that we are considering is external Compton, so we can model external Compton with this code as well. Already there's built into the code external component from the cosmic microwave background. We would like to extend this further and include radiation from our accretion disk as well, for example, and other sources that we can model that and see. I would like to end my presentation. Thank you very much.
All right, thank you, Isaac. We have time for one quick question from the room, if there is any, and there is a question also on the chat. Any question from the room first? People in person? Okay, Isaac, there is a question on the chat by Sambatra, which says, is the method used similar to the smooth particle hydrodynamics, which is also a Lagrangian approach?
So no, this is a different way of doing it. So we're using grid-based hydrodynamics instead of smooth particle. And the reason for that is that we can resolve sort of shock fronts a lot better. And we also have more information in sort of low density environments. And then the sort of particles that we're injecting is sort of tracer particles inside your grid-based fluid.
Okay, thank you. I've got one question. I noticed you didn't include the centripetal motion. It doesn't seem that your jet is rotating outward, carrying away angular momentum. It seems to be a linear projection of the jet. Is that the assumption in your model? And the second question is, what informed your decision to use magnetic field strength of 1 microgauss? I guess it should be orders of magnitude higher around the radio galaxy, right?
Yes, so originally, if I can answer the magnetic field question first, we had simulations without the magnetic field, just RHD simulations. And so we wanted to keep the magnetic field comparable. And in those simulations, we assumed sort of equipartition. And when we went and did the calculations, it worked out that in that simulation, it was on the order of a microgauss. And so we tried to keep it the same for this specific case, that we can compare how our sort of emission assumptions compared between the two models that we have. So in the future, I would like to sort of adapt this and have it a little bit closer to what we get from actual observations. And then in terms of the angular momentum, so in this case, the velocity of the jet is purely in our Z direction. So there's no rotation or anything like that we're considering with this model. Of course, this is sort of just a test case, which we are still testing all of the sort of things we can do. So in the future, we are looking at doing a little bit more complex analysis of these models.
Okay, good. I'll leave you to respond to the question by Zubida online. Zubida said, how are the macroscopic MHD equation related to the microscopic terms? So if you could respond that on Zoom, that would be appreciated. Thank you very much.
So in terms of
can we stop and move to the next talk? Maybe you just write the responses to the chat message, please.
Sure.
All right, thank you very much. Let's thank him again, please. Okay, so the next speaker is Tombo from University of Antananarivo, and she will speak to us about an interesting radio galaxy in the MIGHTY project done with Meerkat. Tombo, you have 12 minutes to speak. I will notify you when it's 2 minutes, and then we'll take questions with remaining 3 minutes. Could you share your screen, please?
Thank you, James. Can you hear me?
You seem to be muted. We cannot hear you.
You can't hear me now?
Not really.
Maybe not. Maybe now you can hear me?
Yes, now we can hear you.
Okay. Okay, so thank you, James, and hello, everyone. And I'm Tum, I'm from Madagascar, and today I'll present our work entitled
Can you share
Mighty.
your screen, please?
Sorry. Okay, I'm sorry. So I will present our work entitled Mighty, revealing the radio properties of J0224.2-0528, a giant radio galaxy in the XMM-LSS early science field. So we can classify radio galaxies in several ways, such as according to their morphologies, or if we consider their nuclear activity, they can be classified as active, remnant, and restarted. And in the case that we consider their size below 0.7 megaparsec, they are considered as normal, and over 0.7 megaparsec, they are considered as giant radio galaxy. So these GRGs can reach up to few megaparsec scales, which is more than 30 times the size of Milky Way. And the first GRG was discovered in 1974, and in 2008, another larger one of a size of about 5 megaparsec was discovered, and it is the largest known GRGs until this year. In fact, another GRG of size of at least 5 megaparsec was discovered and published last month. But what are the reasons that enable these GRGs to reach this huge size? So from past studies, there are three major reasons thought to be responsible for GRG size. So the first is that perhaps GRGs host most massive black hole, but as this first diagram here shows, which is from a recent study, it seems like GRGs and normal arches have the same black hole distribution, but GRGs have a smaller accretion rate, as the second diagram here shows. And the second reason thought to be behind GRG size is that maybe they reside in a less dense environment, therefore they can grow up to these megaparsec scales. And this is more or less confirmed by observations, because there are only 10% of GRGs that reside in dense cluster environment. And the last reasons behind GRG size is that they might represent the oldest populations of AGNs. However, the GRGs and normal arches have the same spectral index. And if GRGs represent the oldest population of AGNs, then there should be more GRGs than currently known. Therefore, we can say that there is no single factor behind GRG size, but a combination of multiple ones, and more detailed studies are needed to disentangle the right scenario. But why are we interested in GRGs? So GRGs are relevant because they represent the single largest astrophysical objects in the universe, and they will help answering the question how certain AGNs can produce such complex and giant structures. And also, GRGs are believed to give possible clues on the black hole accretion process, and also to provide a better understanding of AGN feedback. And moreover, GRGs are still rare compared to normal sized GRG. There are only 1,000 GRGs discovered so far, which is only 5% of overall radio galaxies. And also that most of these small fractions are in the northern sky. Therefore, in this work, we are interested in a giant radio galaxy in the southern sky, which is located in the XMM-LSS field. And as you can see, this field is really rich of ancillary radio data. And moreover, it has been observed by the Meerkat telescope under the project Mighty, which is one of the large-scale projects of Meerkat. And the MIT Continuum Early Science data comprise observations of the XMM, LSS, and the Cosmos field, and it has 20 other approved early science projects. Among that is a systematic search for GRGS and a systematic search for remnant and restarted GRGS. And this giant radio galaxy that I'm presenting here is, we noticed it when we proceed to the systematic search for remnant and restarted the RGs by using the MIT data with a higher sensitivity of 1.5 microjansky. So this GRG that I'm presenting here is located at the spectroscopic redshift of 0.7, and its linear size falls between 0.8 till 1.1 megaparsec, and it has a radio power of 4.6 times 10 power 26 watt per hertz. And here above, we present its radio contour above 3 sigma at 150 megahertz here and at 1.4 gigahertz. And as you can see, its morphology is more extended at 150 megahertz, and it has an edge brightened structure, which suggests that a classification of ether2, and we didn't detect any compact core at the center, but we found a local prominence of 10 power minus 4. Therefore, these morphological features that we observed is typical of remnant radio galaxies or ether2, but with a paired core. Therefore, we conducted further analysis to know the other radio properties of the source. And here we present the spectral index map of the source. And these two maps here show the same features in the location of the galaxy here. And if we refer to the color bar, we can see that the northern and the southern lobes have similar index, but the central region here is deeper than the lobes. Therefore, we can say that it suggests the presence of backflow of radioplasma and the presence of hotspot from past activity. And this index steepening towards the center have been observed in other sources, such as in this remnant radio galaxy here. And as I said, these two maps here show more or less the same features, except this one, the second map. In the second map, the radio galaxy is surrounded by steep emission, which could be interpreted as artifact, because to produce the second map, we have introduced a flux upper value for the pixels undetected in my tube of 3 sigma, or maybe they are a real imprint from the past radio emission. And we have also computed the magnetic field of the source, and for a size falling between 0.8 till 1.1 megaparsec, and the frequency break occurring between 150 megahertz and 1.4 gigahertz, we found a magnetic field ranging from 1.8 till 3.2 microgauss, and these values are typical of remnant radio galaxies. And then we have used this magnetic field to compute a first order estimation of the synchrotron age of the source, and we found age ranging from 13 till 48 megayear. And here is the radio spectrum of the source from 150 megahertz till 1.5 gigahertz. And then we have used this data point when we did the preliminary fitting with rats, and you can see the result that we found tabulated here, and we have used 2 different models. And then we attempt to assess the host environment of our GRG, and we have used image and redshift from SDSS, and based on available photometric and spectroscopic redshift, it seems like our GRG resides in a less dense environment, and its closest neighbor galaxy is located at more than 2 arc-minutes away from it. And then we have used also optical and X-ray catalogs, optical and X-ray cluster catalogs, and we found that our GRG is not associated to any cluster of galaxy compiled in those catalog. And here we have overplot our source on top of PD diagram of GRGs reported by W. et al. 2020. And as you can see, unlike these two GRG discovered in the mighty cosmos early science, our source is not located in a previously unoccupied part of this diagram. Therefore, we have overplot of a remnant GRG, and it seems like they are not clustered anywhere in the diagram. And note that one of these GRG, remnant GRG from literature, this one in green, was discovered in the XMMLSS field. Therefore, we have compared our source with the source, and it seems like in terms of size and other properties, they are similar. But one of their big difference is their spectral index, as you can see in this map. And if you and as you can see, the source is steeper compared to ours, and maybe the steepness is relative to its high redshift of 1.3. Therefore, to summarize my talk, the aim of our work is to report the radio properties of a GRG in the mighty XMMLSS early science field. And we found that the spectral map index of this GRG suggests the presence of backflow of radioplasma and an imprint from past radio emission. And we found that its magnetic field is typical of remnant radio galaxy, and it resides in a less dense environment. Therefore, we conclude that our source is either a GRG, but which core have recently switched off, or maybe it's a restarted giant ether-2 with a buried core. Therefore, we wish that there would be data at higher frequency, that we can explore the properties of our source in these higher frequencies, and we will be able to disentangle the true nature of this GRG. And we will plan to submit a paper reporting this work, which is based on my MSc thesis that I completed last year. And therefore, I am looking for opportunities to pursue PhD. So if you have any suggestion or advice, please do not hesitate to contact me in this email address. So thank you so much for listening.
Thank you very much, Tombo. Questions from the room? Anyone? Okay. Please use the mic.
Thank you for your nice presentation and also the advertisement you made. My question is the index, north, south, and of course the average. There is a mismatch. You see the south and the average is almost the same. There is something you have to look at that one. All right. Some of the indexes.
Your question is on the spectral index?
All right, yes, she has to look at.
Can you share the slide on your
okay, yeah, of course. You can go to from the last second one.
You mean this?
Yes.
From the last second, okay, go down. Go. Go, I will show you.
Yes.
Yeah, yes, of course, this one. Total, north, south, you see? Yeah. Basically, the total must be the around average, and there is.
I'm sorry. So I don't know if I understand your question, but the total is when we take the total flux of the source to compute the spectral index. And for the north and south is we only take the flux of the north and southern lobes to give this value. I don't know if that answers the question.
Okay. All right. It's not.
Okay. Any other question? I do have one, Tombo. The spectral index map you showed, my guess is that this is Meerkat in-band spectral index. Is that correct? You use sub-band images within Meerkat to derive your spectral index.
Actually, we have used observation from LOFAR and MIT, but not sub-band of Meerkat.
Okay. I'm just a bit concerned about the values of the spectral indices. They seem to be more of positive values. Is that really what you see?
Actually, we can, based on the definition of your spectral index, you can use a positive or negative spectral index, actually.
Okay, so you use the positive sign
Yes.
instead. Okay, and what RMS cutoff did you use for the Meerkat contribution side for the spectral index?
I'm sorry?
Remember, you have to flag some signal. You have to flag some bands that are very noisy with a lot of RMS. So what cutoff did you use to flag bad data that you didn't use for the spectral index calculation?
Actually, we have used already flagged data by Jan Haywood, and we haven't did any further flagging, actually.
Okay, maybe we can take this offline. Let's thank
Okay.
Tombo again. Okay, so incidentally, we don't have the other two presenters for this session, which is Eugene and Evaristus. So I guess we can proceed to tea break, but let's thank once more all the presenters who showed up. Thank you very much. And is there any announcement before we go for tea break? I guess none. Here it says tea break. But it should be lunch break. But, yeah. Okay, let's see. The organizers will come give us some announcements later.